Every spacecraft we've ever built would eventually die if it left the solar system for good. Not from running out of fuel, but because something essential would break, and no one would ever come to fix it. The International Space Station, our most complex machine in orbit, survives only because of constant resupply runs, software fixes, and a small army of engineers on the ground, watching its every system. Push that station past Mars, past Jupiter, past the outer edge of the Sun's influence, and every one of those lifelines vanishes. A true starship wouldn't need to survive for months. It would need to survive for decades, centuries, maybe longer, with nothing behind it but the memory of home. So today, we're asking the one question that matters more than speed. How long could a real starship actually survive out there? Think about the longest any machine has ever run without a single human hand touching it for repair. Not a satellite coasting silently with no moving parts. Not a monument standing still in a field, untouched because it never had to do anything in the first place. A real machine, the kind with fluids moving through pipes, electronics firing commands, and mechanical parts grinding against each other every second of every day. The honest answer is measured in decades, at best. Voyager 1 is still out there to prove it. Launched in 1977, it's still transmitting nearly 50 years later, the most distant object humanity has ever built, drifting through interstellar space at roughly 17 kilometers every second. But look closer, and the achievement starts to look fragile. Voyager is the size of a small car. It carries no crew, no water, no food, nothing alive that needs protecting. Its power source, a small chunk of decaying plutonium, produces barely enough electricity to light a couple of household bulbs, and that number shrinks a little more every year. Engineers have already switched off most of its instruments just to keep its faint signal reaching home. A single message sent from Earth takes over 22 hours to arrive, and the reply takes another 22 to come back. Voyager is without question the most successful deep space machine we've ever built, and it is still just a tiny, crewless whisper compared to what a real starship would demand. Now multiply that complexity by 10,000. A starship isn't a probe with no one aboard, and it isn't a capsule with a return ticket built into the plan. It's a vessel meant to cross the space between stars and still be capable of something when it gets there. That word, capable, is where the real difficulty hides. Drifting through space costs nothing. Once you're moving, you keep moving forever, whether anything on board still works or not. A dead ship travels at exactly the same speed as a living one. The difference between a starship and a coffin was never about velocity. It's about whether the ship can still make power, still shield the people inside from radiation, still grow food, still know where it is in the dark, and still slow down when it finally reaches something worth stopping for. Lose any one of those abilities, and the ship stops being a starship. It becomes wreckage, still moving, still following a perfect trajectory toward nothing. We already have a preview of how hard this is, and it's floating just above our heads. The International Space Station is the most advanced home humans have ever built off-planet, and it still needs help constantly. It orbits only about 400 kilometers up, close enough that Earth's magnetic field wraps around it like a shield, deflecting most of the radiation that would otherwise reach the crew. Cargo ships arrive multiple times a year, carrying food, water, spare parts, and equipment. Astronauts typically stay 6 months to a year before coming home to gravity, fresh air, and hospitals. Behind them sits an army of engineers on the ground, watching every system in real time, ready to diagnose a problem the moment it appears. And even with every one of those advantages, the station systems still strain. Pumps fail, filters clog, coolant lines develop slow leaks that take weeks to track down. The equipment that scrubs carbon dioxide from the air has needed repeated hands-on repairs. The system that reclaims water from the crew's own waste is remarkable, recovering close to 98% of it, but that missing fraction still has to be shipped up from Earth. Every one of these systems works because the planet is right there, 400 kilometers away, watching, listening, ready to send help. A real starship would need to do everything the station does and then keep going. It would need propulsion capable of reaching relativistic speeds, then decades of coasting in complete silence. It would need to navigate without any ground stations to check its position against, grow enough food to feed a crew for the entire voyage, shield them from radiation far beyond anything Earth's magnetic field provides, manufacture its own replacement parts, and treat its own medical emergencies with no hospital to call. And it would need to do every part of this with absolutely no outside help. No cargo ships, no updates from mission control, no spare part arriving because someone back home noticed a problem. Nothing arrives. Nothing fixes itself unless the people inside fix it, using only what they carried with them the day they left. There's a kind of ladder to how difficult space travel becomes, and most conversations about Starship skip straight past it. Low Earth orbit, where the station sits, is the easiest rung. Help is close, communication is instant, and the planet's magnetic field does most of the shielding for free. The Moon is a small step up farther away, but still close enough that if something goes seriously wrong, the crew can usually come home. Mars changes the nature of the problem entirely. Depending on where the two planets are in their orbits, a message can take anywhere from 4 to 24 minutes to arrive one way, and a full round-trip mission can take 2 to 3 years. For the first time, medical emergencies can't be solved by evacuation. If something goes wrong far from Earth, it gets treated with whatever is already on board, or it doesn't get treated at all. But even Mars is still inside the solar system. Sunlight still reaches it. Communication, however delayed, still works. The crew still knows deep down that they are eventually coming home. Interstellar space isn't the next rung up that same ladder, it's an entirely different one. Past the edge of the solar wind, our sun shrinks down to a single point of light, indistinguishable from any other star in the sky, and solar panels stop producing anything useful. A message sent home might not return an answer for years or decades, arriving long after the people who sent it have changed beyond recognition. There is no resupply, no rescue, no possibility of turning back. A starship breathes, not in any biological sense, but in a way that's just as fragile and just as fatal if it ever stops. Every sealed space carrying human beings has to continuously pull carbon dioxide out of the air they exhale and replace the oxygen they use up. It sounds simple, it isn't. At around 1% carbon dioxide concentration in the cabin, people start getting headaches and struggling to concentrate. At 2%, judgment and decision-making noticeably decline. At 5%, dizziness and confusion set in. Past 8%, unconsciousness can follow within minutes, and death shortly after. The difference between a functioning starship and a dead one can come down to a scrubber running just a few percent less efficiently than it did a decade earlier. On the International Space Station, this balance is kept using chemical scrubbers and filtering beds, packed with a material that slowly loses its ability to absorb gases and has to be periodically replaced with fresh stock flown up from Earth. A starship doesn't get that delivery. Whatever scrubbing material it carries at launch, or whatever it can manufacture on board, is all it will ever have for the rest of the voyage. Oxygen brings its own version of the same problem. It's typically produced by splitting water molecules apart, a process that depends on a steady supply of both electricity and water. If either one drops even slightly below what's needed, oxygen production quietly falters. The crew doesn't suffocate suddenly. They suffocate gradually over weeks, as the air slowly becomes a little less able to sustain conscious activity than it was the week before. The air on board isn't something you load once at launch and forget about. It's a living balance, a chemical tug of war that machines have to keep winning every single hour for the length of the entire voyage. Every breath the crew takes nudges that balance slightly out of place. The machines exist to pull it back. If they slow down, even a little, there's no outside air to dilute the problem. The atmosphere is either maintained or it isn't. There's no comfortable middle ground. Water tells a similar story, just as unforgiving. A single person needs roughly 2.5 to 3 litres of drinking water a day, before counting what's needed for food preparation, hygiene, and growing crops. The International Space Station recycles urine and cabin humidity back into drinking water through a chain of filters and catalytic processes, reaching close to 98% efficiency, an extraordinary number. But that remaining 2% still has to come from Earth, delivered on the next cargo flight. A Starship can't outsource that 2% to anyone. Whatever water it launches with is the total supply for the rest of the journey. Even a system that starts at 98% efficiency will slowly lose ground as filter membranes wear, and catalytic material loses its potency over decades. Losing just 10% of your water with every cycle might be manageable over a few months, drawn down from reserves. Stretched across decades, that same small loss becomes the difference between comfortable margins and running dry. And water isn't only for drinking. It cools the ship's machinery through thermal loops, feeds the chemical process that generates breathable oxygen, and in some proposed designs, even helps shield the crew from radiation by forming a kind of liquid wall around the living spaces. It's the base ingredient for most of the ship's chemistry, and the growth medium for whatever crops are being raised on board. Lose your water, and you don't just lose something to drink. You lose cooling, oxygen production, food and shielding, all at the same time. Feeding a crew for decades brings its own kind of math that quickly turns brutal. A single person eating 2,000 calories a day needs something like 700,000 calories a year. Multiply that by a crew of 100 people across a 50-year voyage, and the total climbs into the billions of calories, all of which somehow has to exist on board in a form that hasn't rotted, spoiled, or lost its nutritional value by the time anyone actually eats it. Carrying all of that food from departure simply isn't possible past a certain point, both in terms of mass and shelf life. Freeze-dried rations lose vitamins over years of storage. Fats inside them slowly oxidize. Proteins lose their nutritional value. A crew eating 20-year-old meals might technically have food sitting in front of them, without getting anything close to the nutrition their bodies actually need. The alternative is growing food on board, using hydroponic or aeroponic systems lit by artificial light, powered by the ship's own reactors, doubling as a way to pull carbon dioxide out of the cabin air and put oxygen back into it. It sounds elegant on paper. In practice, crops grown in the enclosed low-gravity conditions of a spacecraft have shown stunted growth, lower yields, and in some experiments, a failure to produce viable seeds at all. A Starship's farm isn't a garden. It's a biological machine that has to produce a specific caloric and nutritional output every single day for the length of the entire voyage. A contaminated crop, a lighting system failure, a nutrient imbalance in the growing solution, or even a subtle shift in the air composition inside the growing chamber can trigger a shortage that takes months to recover from. And during those months, the only food available comes from reserves that are finite and can't be replaced. None of these systems run on their own separate schedule. They're tied together in ways that make one failure ripple straight into the next. Less power available means the water recyclers run at reduced efficiency. Less clean water means weaker, less productive crops. Weaker crops mean a hungrier, more fragile crew, with less physical energy and fewer healthy hands available to fix whatever breaks next in line. This is the part of the story that rarely makes it into the popular imagination of a Starship voyage. Not fire, not explosions, not one dramatic system failure that ends everything in an instant. Just a slow, quiet erosion. A scrubber running a little worse than last year. a filter clogging a little sooner than expected, a crop yielding a little less than it used to, until one day the comfortable margins the crew started with simply aren't there anymore, and nobody can point to the single moment it happened. Radiation is the threat that never takes a day off. Inside the shelter of Earth's magnetic field, the planet blocks most of what the sun throws at us. Step outside that shelter, out past the edge of the solar wind, and the danger changes character entirely. Out there, the main hazard comes from galactic cosmic rays, particles flung across the galaxy by exploding stars and other violent events, travelling at incredible fractions of the speed of light. These aren't gentle. Protons, helium nuclei, and heavier atoms slam into anything solid with enough energy to punch through meters of material. Here's the strange part. Piling on more shielding doesn't always help. When one of these high-energy particles hits a thick barrier, it can shatter on impact, spraying a shower of secondary particles inside the ship that can be just as damaging as the original strike. Past a certain thickness, more shielding can actually make the radiation problem worse, not better. Even with the best shielding materials available, the dose a crew absorbs in interstellar space stays far above anything considered safe for astronauts today. Over a journey lasting decades, the cumulative exposure adds up to multiple times the career limit currently set for anyone flying in Earth orbit. This isn't a spike that passes, it's a permanent condition, more like standing in a hailstorm that never lets up, where the hailstones are invisible and pass straight through the walls around you. Nobody drops dead from this all at once. Instead, cells absorb damage a little at a time. Most of it gets repaired automatically by the body's own machinery, but not all of it. Over years, the errors accumulate. Cancer risk climbs. Cataracts form earlier than they should. The crew doesn't collapse. They simply age faster, get sick more often, and lose resilience, a little more with every year spent outside the sun's protective bubble. Powering all of this is its own separate nightmare, because every solution runs into a wall eventually. Solar panels work beautifully near Earth, but their output drops off sharply the farther you travel from any star. Past the outer planets of our own solar system, sunlight becomes too weak to run anything demanding. In interstellar space, there is no sunlight at all to catch. That leaves nuclear power as the only real option humanity has ever actually tested for long-duration missions. Small generators that convert the heat of decaying plutonium into electricity have kept probes like Voyager alive for decades, but their output is tiny, and it shrinks on a predictable schedule as the fuel itself decays. After about a century, one of these generators produces roughly half the power it started with. A starship needs kilowatts or megawatts running continuously. A trickle of decaying plutonium isn't going to cut it. Nuclear reactors offer far more power, but they come with their own expiration date. Reactor fuel is finite. It has to last the entire voyage, plus a safety margin, because there's no way to refuel partway through. The components inside a reactor swell and degrade under constant radiation. Coolant lines corrode slowly from the inside, and the longest-running reactors on Earth, maintained by entire industries of trained specialists, have only ever managed to operate reliably for around 40 to 60 years. Fusion power, the same process that powers the sun itself, would theoretically solve this problem cleanly, offering enormous energy from a small amount of fuel. But after more than 70 years of research and billions of dollars of investment, humanity still hasn't achieved continuous, practical fusion power here on Earth. Saying a starship will simply run on fusion is, right now, a statement of hope rather than engineering. Underneath all of this system sits a quieter problem that's just as dangerous: keeping the machinery itself running. Every mechanical part on board has a finite lifespan. Bearings wear down. Seals lose their flexibility. Valve components corrode. Circuit boards slowly accumulate radiation damage. lubricants break down chemically and stop doing their job. Every one of these failures is in a sense predictable. Engineers can estimate how long a given part should last before it breaks, but stocking spares for every single component that might fail across a 50-year voyage or a 500-year one quickly becomes a problem of space and weight that no cargo hold can solve on its own. 3D printing offers a partial answer, letting a ship manufacture replacement parts from raw materials stored on board instead of carrying every spare part it could ever need. But printing a functional-looking part isn't the same as printing one that performs identically to the original. High-stress components like pump parts or pressure vessel fittings need precise internal structure that current printing technology still struggles to replicate reliably. And manufacturing anything requires expertise, not just equipment. Someone on board has to know how to design the replacement, choose the right material, run the printer correctly, and inspect the result for hidden flaws. That knowledge has to be passed down, generation after generation without gaps. If the one person who understands the fabrication system dies before training a replacement, that entire capability can quietly disappear from the ship. Even the empty space between stars turns hostile at the speeds a starship needs to travel. Interstellar space isn't a perfect vacuum. Scattered dust and stray atoms drift through it, and at even a few % of the speed of light, a single speck of dust becomes a projectile carrying the force of a bullet. Multiply that across decades of travel, and the ship's forward hull absorbs thousands, possibly millions of tiny impacts, each one eroding shielding and pitting structural surfaces just a little more. None of these problems arrive as a single dramatic crisis. A reactor doesn't explode, a shield doesn't shatter all at once. Instead, everything wears down together, quietly, in parallel, each small failure making the next one slightly more likely, until the ship that once had comfortable margins for survival is left running closer and closer to the edge of what keeps a crew alive at all. Medicine on board a starship has to cover every possible ailment a human body can develop, without any of the infrastructure that makes modern medicine work. On Earth, even a broken bone gets treated in a hospital, backed by imaging equipment, sterile operating rooms, and a supply chain stretching across the entire planet. On a starship, that same injury gets treated by whoever on board has the most medical training, using whatever equipment happens to still be functional. The crew's medical needs will also shift in ways nobody can fully predict before departure. Genetic conditions may surface in children born during the voyage. Nutritional gaps may emerge if the food production system can't maintain a complete dietary profile for decades on end. Psychological strain, depression, anxiety, and interpersonal conflict have to be managed in a place where no one can ever be sent away to get space from the situation. Medications themselves quietly betray the crew over time. Most drugs are only tested for stability across a handful of years, under carefully controlled storage conditions here on Earth. Aboard a starship, radiation accelerates the breakdown of complex molecules, temperature swings stress chemical bonds, and humidity shifts in recycled air alter how compounds dissolve. Some antibiotics lose more than half their strength within just 3 or 4 years, even in ideal conditions. Insulin is famously sensitive to temperature and can't survive long-term storage without precise refrigeration, that itself has to be maintained and powered for the entire voyage. Emergency medications degrade on similarly short timelines. A crew facing a medical crisis decades into the journey may open the pharmacy locker to find the exact drug they need has already broken down into something closer to useless. Surgery adds its own layer of difficulty. A moderately complex procedure on Earth calls for a full team, a surgeon, an anesthesiologist, sterile instruments, and a room built specifically for the job. On board, the same procedure might be handled by 1 or 2 people, who also serve as engineers or farmers on other days, working in a space that doubles as a lab on any other afternoon. A single surgical mistake can cost the ship a person whose expertise in some other critical system may be impossible to replace. There's a slower, generational threat hiding underneath all of this too. A crew of even several hundred people represents a very narrow gene pool. Across multiple generations confined to the same close population, rare genetic conditions become statistically more likely to appear, and the immune diversity that normally helps a population fight off new diseases gradually narrows. It's a problem that has to be managed deliberately, generation after generation, in ways no human society has ever had to consider so carefully. Finding your way through interstellar space brings a completely different kind of difficulty, one that has nothing to do with fuel or fatigue and everything to do with geometry. Near Earth, a spacecraft can check its position against the Sun, known planets, and ground tracking stations. None of that exists once you're years into an interstellar crossing. There's no satellite network to check against, no ground station pinging back a location. Instead, the ship has to measure the angular position of distant stars and compare those readings against a stored catalogue, essentially triangulating its location using starlight alone. The problem is that this geometry shifts as the ship moves. Stars that made perfectly reliable reference points at departure slowly change their apparent position as the ship's own perspective shifts across light years of travel. A small, uncorrected error in how one of those reference stars is expected to move can quietly compound into a navigational drift of millions of kilometers over the course of a decades-long crossing, and the sensors doing the measuring aren't immune to the environment either. Optical detectors accumulate radiation damage over time, individual pixels fail, and dust impacts slowly cloud the lenses and mirrors used to take these star readings in the first place. Without any outside reference point to check against, the crew can't always tell whether an apparent course deviation is a real drift, or just a sensor slowly losing accuracy. Correcting for a problem that doesn't exist can be just as dangerous as ignoring one that does, and either mistake compounds quietly over years before anyone notices. Computers face a parallel kind of slow decay. Out past the shelter of any planet's magnetic field, high-energy particles strike computer chips more often, occasionally flipping a single bit of stored data or corrupting a calculation mid-process. Engineers can guard against this with error-correcting memory and redundant systems, but over decades, the cumulative radiation damage still degrades the underlying hardware. Processors run slower to remain stable. Storage systems slowly accumulate errors. The ship's entire computing infrastructure becomes gradually less trustworthy, right at the point in the mission when accurate navigation and system monitoring matter most. And then there's the strange paradox facing the propulsion system itself. Many Starship designs call for a period of intense acceleration, followed by years or decades of complete silence, while the ship simply coasts, followed eventually by an equally intense deceleration burn near the destination. But mechanical systems don't sit idle well. Residual fuel left in engine lines can slowly decompose into deposits that clog injectors. Seals that maintained pressure perfectly at launch can turn brittle in the vacuum of space, developing microscopic cracks that spread invisibly, year after year. There's no way to test fire an engine partway through an interstellar crossing without burning through fuel the ship can't spare. The crew simply has to trust that a system which last ran decades earlier will perform exactly as designed the moment it's finally called on again. A propulsion system that worked flawlessly on departure day may simply refuse to ignite after decades of cold, silent, irradiated dormancy, and if that happens during the deceleration burn, every year of careful survival that came before it collapses into a single mechanical verdict. The stars don't arrange themselves for our convenience. They sit at distances that have nothing to do with how far we can travel, or how badly we want to reach them. And once you start listing those distances out loud, the true weight of an interstellar voyage becomes impossible to ignore. Alpha Centauri is where every conversation about starships begins, because it's the closest star system we have, sitting a little over 4 light-years away. At 10% of the speed of light, a velocity far beyond anything humanity has ever built or is currently funding, the journey there would take roughly 44 years. That's almost a single human lifetime, the one interstellar target where the original crew might actually live to see the destination with their own eyes. But 44 years of flawless operation for every system on board isn't a modest engineering goal. It's an unprecedented one. No sealed life support system has ever been tested for that long. No spacecraft reactor has ever run that long without a major overhaul. And even if the ship survives the journey intact, the planet waiting there, a rocky world orbiting the system's small red dwarf, is likely locked with one side permanently facing its star and the other in permanent darkness, regularly blasted by intense stellar flares that may have stripped away any atmosphere long ago. Barnard's star sits a little under 6 light-years out, adding 16 more years to the trip, 16 more years of wear on every seal and bearing, 16 more years of accumulated radiation, and there's no confirmed habitable planet waiting there at all, just disputed hints in the data. A crew could spend 60 years of their lives reaching a destination that turns out to hold nothing worth the sacrifice. Sirius, the brightest star in our night sky, sits at roughly double the distance to Alpha Centauri. At the same cruising speed, the journey stretches to about 86 years, long enough that the crew who launch the mission will not be the crew who arrive. Their children, or their children's children, will be the ones who finally see the destination, inheriting a mission they never chose to be part of. Tau Ceti pushes the number past 120 years, meaning grandchildren rather than children become the ones stepping off the ship at journey's end. By now, an entirely new problem has entered the picture, one that has nothing to do with machinery. How do you keep a small sealed community functioning across multiple generations, teaching engineering, medicine and navigation to children who are born inside the hull and have never seen an open sky? Vega, one of the brightest stars visible from Earth, sits about 25 light-years out, meaning roughly 250 years of travel. Look back 250 years into our own history, and you find a completely different political map, different languages, a different scientific worldview entirely. A starship aimed at Vega has to accept that the civilization which launched it will be unrecognizable or gone by the time anyone arrives. Polaris, the North Star that guided sailors for centuries, sits somewhere between roughly 300 and 400 light-years away, depending on which measurement you trust. At cruising speed, that's a journey of more than 3,000 years, longer than the entire span of recorded human history from the fall of ancient empires to today. No language, no government, and no institution has ever lasted that long. Whatever culture exists aboard the ship by the time it arrives would share almost nothing with the people who built it. The 7 rocky worlds orbiting the dim star known as TRAPPIST-1 sit around 40 light-years out, close enough that 3 of those planets fall within a zone where liquid water could theoretically exist. It's the most planet-rich target within reach that we know of. But the journey there takes roughly 4 centuries, longer than the entire history of most nations on a map today. At that scale, the ship stops being a vehicle. It becomes a civilization, one that has to govern itself, educate its own children, and keep growing food across 400 years of continuous operation with absolutely no outside contact. Betelgeuse offers a different kind of warning entirely. It's a massive, unstable red supergiant more than 600 light-years away, already showing signs of nearing the end of its life, expected to explode as a supernova at some point that could be tomorrow, or could be 100,000 years from now. A journey there would take over 6,000 years. long enough that the star itself might not even exist anymore by the time anyone arrived, replaced instead by an expanding cloud of superheated debris from an explosion that happened centuries earlier. There's an even stranger case worth mentioning. A modest, unremarkable star called Gliese 710 currently sits around 60 light-years away, but it's actually moving toward our solar system, and in roughly 1 million years it will pass remarkably close enough to briefly outshine every other star in our sky. It sounds like a gift, a star coming to meet us halfway. But waiting for it isn't a strategy. 1 million years is longer than our entire species has existed in its current form. Whatever exists on Earth by the time that star arrives will have nothing in common with us at all. Each additional light year multiplies every problem that came before it. The radiation dose climbs, mechanical wear accumulates, spare parts run thinner, the population aboard changes hands from one generation to the next, carrying knowledge that has to survive being passed down without a single gap. And at every single one of these distances, the same question keeps resurfacing, more urgently each time. Is whatever waits at the destination actually worth what it costs to get there? Because reaching a star, even the nearest one, was never really about crossing a distance. It's about whether a sealed loop of machinery and biology can hold together for as long as that distance demands, and whether the people trapped inside it can keep believing the destination is worth the wait, long after the world that sent them has moved on without ever knowing if they made it. Suppose everything holds. The reactor runs clean for a century. The water recycler never drops below the margin it needs. Crops keep yielding, shielding keeps holding, and somehow, after decades of silence, the propulsion system fires exactly as designed. Against every likelihood, the ship arrives. Now ask the harder question. Does anyone still care that it did? The civilization that built and launched a starship existed at one specific moment in history. It had its own politics, its own priorities, its own reasons for believing the mission mattered. It funded the ship, trained the crew, and watched it shrink into a point of light before vanishing into the dark. Everything that happens afterward unfolds without that civilization ever watching in real time again. Status reports still trickle back to Earth in the years following departure, delayed a little more with every passing year. The first ones make headlines. The next round draws academic interest. By the 10th report, an entire generation on Earth has come and gone. Political leaders who championed the mission have been replaced. The agency that built the ship has been reorganized, or defunded, or simply forgotten. New telescopes, far more powerful than anything available at launch, may have already imaged the destination system in more detail than the ship's own instruments will ever manage up close. Earth has been living without the mission for decades by the time the ship reaches its halfway point. Families of the original crew have aged and passed on, succeeded by descendants who never met the people who left. What was once an urgent, defining mission quietly becomes a historical footnote, a relic of a previous era's optimism still transmitting faintly, no longer occupying any real place in anyone's daily thoughts. That's the optimistic version of events. Wars, pandemics, or economic collapse could just as easily hit Earth hard enough to break the very institutions responsible for listening for the ship's signal in the first place. If that support disappears, the ship keeps transmitting into total silence, with no way of ever knowing that nobody is listening anymore. Or Earth could leap forward instead of backward. A breakthrough in propulsion technology, discovered decades after the original ship departs, could allow a second, faster mission to catch up and even overtake the first. The new ship reaches the same destination years, or centuries, before the original crew ever gets there. Physicists have actually worked out the math behind this exact scenario, and for many distant targets, the coldly rational choice isn't to launch today at all. It's to wait for better engines, because the time saved by waiting can outweigh the head start of leaving early. Imagine the weight of that. A crew spends their entire lives, and their children's lives, keeping a ship alive across a void, only to receive a transmission one day confirming that people already arrived, using a vessel that didn't even exist when they first left home. Every year of sacrifice, every generation of careful maintenance, rendered redundant by a civilization that simply waited a little longer and built something better. This is where the real danger of an interstellar voyage stops being mechanical and becomes something closer to spiritual. A human being can endure extraordinary hardship if they believe that hardship serves a purpose larger than themselves. The same principle sits behind every military unit, every polar expedition, every long submarine deployment in history. The mission gives the suffering a frame, and the frame is what makes the suffering bearable. Take that frame away, and the suffering doesn't just become disappointing, it becomes unbearable. A crew that learns their mission has been overtaken by history doesn't simply shrug and carry on. Something in the psychological architecture that held them together, sometimes across multiple generations, starts to give way. Why keep maintaining the water recycler if someone else already got there first? Why keep teaching the next generation the skills the mission requires if the mission itself no longer means anything? A few crews might adapt, finding new meaning in the journey itself or in the small community they've built inside the hull. But history offers little comfort here. Isolated human groups that lose their sense of purpose rarely settle into calm acceptance. More often, the result is conflict, withdrawal, and a quiet unravelling of the discipline that once kept everyone maintaining the ship. And a fracture like that, aboard a sealed vessel with absolutely no way out, isn't a metaphor, it's lethal. Purpose fades naturally across generations regardless, even without that specific blow. The first crew chose to go, understanding exactly what they were leaving behind and why. Their children were born into the mission, but raised by people who remembered Earth firsthand, who could describe open sky and rain from memory. By the third generation, Earth has become nothing but an abstraction, a word in a history lesson, a photograph slowly fading in a digital archive. That generation never chose the mission. They simply inherited it, the same way they inherited the ship itself. So the honest answer to the question this whole journey has been circling is that nobody actually knows how long a real starship could survive, because the experiment has never been run. No machine has ever been asked to function for centuries without a single visit from the outside world. No sealed biological system has ever been tested at that scale for that long. No human community has ever been isolated together for generations with absolutely nowhere else to go. Here's what we do know. A real starship was never going to be defined by how fast it could fly. It would be defined by whether the air stayed breathable in year 80, whether the reactor still ran in year 200, whether the children born in the 3rd century of the voyage still understood why their ancestors ever left home in the first place. The stars themselves aren't going anywhere. They'll burn for billions of years, indifferent to whether we ever reach them, rewarding no one for trying and punishing no one for staying home. The only real question left is whether anything we could ever build, and anyone we could ever send, might actually outlast the distance between us and them. If you like the video, don't forget to leave a like and subscribe. It makes a huge difference and helps the channel grow.